but with the powdered metal, so beyond straw beer, St. Mary's is very much known for their powdered metal.
Really?
Very much known. Just honestly, Pennsylvania in general. I think during World War II they called it the carbon capital of the world because they were doing so much with like graphite and stuff. But it became a huge powdered metal industry with steel and stuff for the automotive. So we'll get into we'll do that quick, and then I'll get to like the actual research. But I did bring some powder.
Yeah.
In to show you. So that's just stainless steel powder. That's not from Pennsylvania. We got that from a commercial vendor, but we're doing research on that. So that powder right there is, roughly on the order of 100 micrometers. So about the thickness of your hair, right? Really, really small. And powdered metal, the reason powdered metal is because certain metals aren't easy to make into shapes when you melt them, right? It's hard to make them into these complex shapes or do high throughput things when you have you're going from a melt, right? You're casting it, you're just pouring it in, letting it cool. So, a big thing is taking powdered metal, filling a shape with it, and just pressing it down, right? Mm-hmm. Pressing it, and then you get the powders really close together, you put it in a furnace, and you sinter it. So then you don't melt it, you just like cause those particles to fuse together. So the basic PM process is you take that powder, you press it into something called a green part. You know what a green part is? That's a green part.
Pre-sintered.
Pre-sintered. And then you sinter it. Nothing. So I'm going to ask you now, go ahead and break that one.
Wait, can I?
Yeah. That's the last one I had. I figured I'd give it to you for a good occasion.
I didn't expect to actually be able to break it.
No, it's just pressed powder. It's literally just pressed powder. It looks, it's easy enough to handle it, but it will break.
It felt like metal. And I was like, oh, break out.
This one, you won't break that one. I mean, this is just... It's amazing, isn't it?
Yeah, what?
So, I mean, this is pressed with, like, thousands of tons. And they have a very complex die to fill all this stuff, right? So, these are courtesy of Keystone Powdered Metal, which is where my dad works in St. Mary's, but they're huge into powdered metal. Automotive is probably the biggest industry for this, right? This is a clutch plate for, like, a Ford transmission, an automatic transmission. And the reason is because you can press one of these every couple seconds and just have a conveyor belt going into the furnace, and you can produce these things on a very, very rapid scale.
That's so weird because it's cold like metal.
Oh, yeah.
It's metal, but...
It looks like it's... Yeah. But that one you're not going to break. That's through the oven, and that's going in a car, basically. Yeah.
Now, why is it that... How can we turn this into this? Like... How does sintering really change everything up? And like, what is sintering? Why do we do it? And how does it affect the powders?
Yeah, so sintering is, again, it's not melting it. It's still all solid. It's just causing the particles to close up the pores between them. It's just, you increase the temperature, you're just causing diffusion. Not to get too technical here
please.
For the non-scientific audiences.
No, the whole point of this is to get as technical as we can.
Okay.
Yeah, get technical here.
Sure. So you heat it up, you cause like surface diffusion on the particles, and you want them to like reduce their surface area, so eventually they just kind of bond in the solid state, and you form a part that's basically 100% dense. And then you get that. So, yeah.
And that's through heat application, or is there other ways of sintering metals?
Sometimes they'll apply the pressure and the heat at the same time. That's like hot pressing. This is cold press. This is just, I guess that part, was pressed from powder very similar to that in a regular press. When I say regular, it's not your lab press. This thing's like 3 stories tall, right? And it's, again, thousands of tons of pressure on like a mold that looks like this, because you have to fill that geometry. And then it's stamping that down, again, apart every couple seconds, and then putting it right into the furnace, right? A lot of it's automated, like robotics. You just fill the powder hopper at the top, and it goes. That does shrink, right? Like I said, that's not perfectly packed, so you also have to account for shrinkage for your final part. But by the end of it, you have a part that is almost 100% dense, right? This is not stainless steel. You can see the rust on there. But it would be lubricated in your transmission, probably. But yeah, a solid part with really good mechanical properties. And the difference between melting, steel melts at 1500 C or something like that. When you're sintering, you're not at 1500. You're probably at 1000 or 8. You're above a certain temperature to tailor the microstructure, right? The structure of the material at the really small scale, but you're not actually melting the material, right? And if you look at this is a pretty complex shape, would you say?
Yeah.
To design something like that with all the teeth and that detail, but you can still see maybe where pressing might not always give you the complexity that you would like, right?
Mm-hmm.
Like, what if I wanted to do... I think the most complex they'll go is they'll do, like, multi-step presses, so sort of like this, but... Or they have, like, actual, like, rotational ones. So say you're doing a torsional gear bearing or something, they can actually turn the press head as it's going down. But what if I wanted to do, like, really thin channels or internal stuff? You can't.
Right.
So I think that is where the hype of additive manufacturing comes in. And that kind of circles us back, I think, to the research. So, like I said, I'm making powder. I was very attracted to come here because of the powder, but it's for totally different applications than a press and cinder part in an automobile, right? So the vision I have for my research is making powdered metal, actually doing the making of the powdered metal, not just saying, oh, I have this powder, how do I turn it into a part? It's how do I synthesize the powder so I can process it so it gives me a really nice part via additive manufacturing, right? One of the biggest sectors that can benefit from additive is space, right? You have very niche parts, very complex parts that can't be fabricated by certainly melt-based, but maybe even conventional press and sinter. So that's really where I see the value of powder in additive manufacturing and stuff like that. Yeah.
What is like an additive manufacturing?
Additive manufacturing is exactly what it sounds like. It's making a part via addition of layers, right? You think of, a part like this might not come out perfect. You might need to do some machining on it, and that would be taking away material or subtractive. But if I was to build this via additive manufacturing, I would build it up layer by layer. And funny enough, the way that metals are additively manufactured still comes from powder, right?
So is that like 3D printing?
Exactly. Synonymous. Well, depending on who you ask, but it's basically synonymous. Yeah.
Gotcha. But what you're talking about is not like, I guess when I think 3D printer, I think of the little plastic things that are like kind of, I don't know, I think they look a little goofy sometimes. Is this, like, do you, like, take these powders and, like, deposit them in the same way, or what's changing here? I guess,
sure.
How are you making these metal parts?
So they are both additive manufacturing, right? Obviously the plastic one went commercial way before metals did. Metals are unique, though. You can't process them in the same way by extruding them through a nozzle. They don't have the properties of a polymer to do that. So what you do is you make them from the powder. You basically spread a layer of powder, you take a laser and raster it over it, and you melt the areas you want to. So if it was this geometry, I'd be melting a 2D area that corresponds to that cross-section. And I would just do that successively, layer by layer by layer, until I get to a solid part. So unlike this, it is actually melting it. It's not melting the whole thing every time, it's just melting the layer. But as you'll see in, I think, the video, you'll see like sparks coming off and, molten powder flying off. It's a really cool process, but it allows you to, again, make really complex parts and rapidly prototype things that, this you would have to engineer a whole tooling set to be able to manufacture that, right? Whereas I can just throw it in CAD and kind of do it with metal additive.
So you have like this machine where you just throw in powder and it just shines a laser and all of a sudden you're able to extract the material?
In simplest form, yes. But the powder is really important. It needs to be flowable, very spherical. When you're pressing powder, it's usually really irregular. So when you press it, it can interlock. And it's also usually very small because then the amount of pores you have to close up is less. But for additive, it's all about being able to spread the powder over the build plate that you're going to put the laser over. Right. Go ahead.
So for laser powder bed fusion.
Yeah, thank you for finally saying the term. Laser powder bed fusion is the official term. Yes.
Yeah, so for powder bed fusion, your research is particularly about manufacturing these powders.
Yeah.
So what's the challenge here? Like, what are you trying to make? Why are you trying to make these powders in these specific ranges.
Okay.
Sphere, like, you know, how spherical it is. Like, just take it away and get technical. Like,
get technical.
Technical.
So let's start with the typical size range for laser powder bed fusion. I mentioned that's about 100 microns. For like press and center, there's probably some big ones, but on the order, you're probably single-digit microns. For laser powder bed, it's 15 to 53 microns or 15 to 45, depending on who you ask. Very discrete size range. You're like, okay, well, what's this? Well, the finer you get, the worse it's going to spread, right? It's going to clump up. It's not going to have that flowability characteristic. And if you spread a powder that doesn't spread well, you're going to have areas that are higher or lower, and your final part's going to reflect that, and it's going to turn out very poorly. If you get any bigger, then you're trading off resolution. So I could print a millimeter size powder. Well, chances are I'm not going to be able to close up the pores, but I'm also limited to the resolution. Then I can only have a wall that's roughly 1 millimeter thick.
Yeah.
But if you have that nice, perfect window, it gives you the ability to tailor intricate details and not sacrifice the flowability, which is, again, going to influence your final part density and details in that manner.
Right. And, like, what exactly can you do to ensure that your powders fall between this 15 to 45 range?
Yeah, that's a good question.
And, like, I guess if I'm making a material out of, like, let's say if I'm trying to, you know, do laser powder bed fusion on titanium, or if I'm trying to do it on niobium, am I going to want, let's say, 20 for titanium to make sure, like, the standard deviation of size is really small, or can it be between that 15 to 45? Is it better to have larger standard deviation, smaller? And then, like, how exactly do you make sure that these powders are in that range as opposed to other ranges?
So I think there's some flexibility, and I think there's research that needs to be done on, like, going outside of that range, because the fundamentals of the process should work the same. Again, like I mentioned, you're just going to trade off the resolution. What you can do is, it's called sieving. It's basically like taking a mesh that's sized, you know, like a square, really small squares that is sized to those specific dimensions you want, and you just sift the powder through it layer by layer, right? And then you collect the powder in the range you want. Now you can see the obvious issue with that is you're wasting a lot of material, right? So manufacturers won't tell you how much they waste, but they'll just send you the cut. They'll send you a 15 to 53, but there's no way what you're putting into the machine is giving you that out. It's a whole, oftentimes, Gaussian type distribution of powder, right? You get a range, and then you take the ones you want. Hopefully you can either recycle or use the other ones elsewhere, but that's not necessarily the case. And the way that powders are made kind of reflects the yield in those ranges and also the utility of it for AM. So like I mentioned, sphericity is also very important, right? If you have finer powders and they spread better, you might be able to get the finer powders to spread better by making them spherical. So conventional powder production techniques, you know, for press and center or that, they don't necessarily give you the best spheres. So we have a technique in our lab called ultrasonic atomization. So atomization is basically breaking up a liquid into droplets, right? A lot of times you process or make powdered metal from the melt, and then you break it apart into small droplets. So atomization is one of the most common ways to produce metal powder. But the mode of atomization, the energy type you're putting into it to cause that breakup, can really influence the shape and size distributions you get. So if you use something like water to hit it, oftentimes it's going to solidify very fast into irregular shapes. That's the type of powder you would use to press and center. If you hit it with gas or something, the cooling rate might not be as fast, but you'll give it more time to solidify and get pretty good spheres. And sometimes you'll get these little, they call them satellites. They're almost like moons clinging to the Earth, right? It's like this little particle on the side that can also compromise flowability and feature resolution. Other methods involve just like rotating them out really, really fast. Generally gives you pretty good spheres. Our method, ultrasonic atomization, I say our, but we didn't come up with it. It's a semi-commercial technique. Now, the method we have in our lab basically takes the molten metal and drops it onto they call it a sonotrode, but it's another piece of metal that's vibrating really fast, like ultrasonic frequency, so almost above what you can hear. So 20,000, 40,000 times a second. And when it hits that, it induces waves into it that break off into like capillary waves at the tips and then come off as droplets that solidify into very, very nice spheres. So that's the method we're using. I think you'll show the video with water. Yeah. So water. That's kind of the demo we did outside of our lab.
Yeah.
It's just recorded with Logan's pretty high. He's got a pretty nice camera on his phone. High res, medium, slow mo video, but it really illustrates the breakup mechanism.
Yeah.
And then the other video is us doing tin. So tin's a very nice one to experiment with because it's a low melting point material, right? It melts at like 220 C. It's, you could almost melt it like with a
boiling water.
Yeah. It's like, that's a good point. Yeah, I never thought of that.
220.
Yeah. So, but that one is like inside of our. Obviously, we don't do this in air. We do this in a contained chamber, and we have a plasma torch coming down as the heat source to melt a rod of metal that then falls onto that vibrating like substrate to cause the breakup. So, yeah, we can melt. I say we did tin, but we've melted up to tungsten. That does 3,400 degrees Celsius, which is the highest melting point metal.
Yeah.
So,
what is a plasma torch?
What is a plasma? That is a very good question. Think of welding, right?
Okay.
Maybe? Does that help?
Maybe.
No?
Yeah.
Plasma is like an ionized gas, basically. So we're doing this process in argon, and if you apply enough electricity between two different electrodes, right, you bias them, you can get electronic interactions between the argon molecules that cause this plasma. It's basically excited argon species, right? So the plasma is not the metal. The plasma is just what's used to melt the metal. All right, the sun's a plasma, right? So this is basically like a welding torch, but it's non-contact. With normal like MIG or TIG welding, you're like touching metal to strike it. This has like an internal arc, and then you just transfer that arc from the torch to the base plate, and then you use that. You control the current and stuff with that to control the heat or the power you're putting in to melt the metal, right? Plasma. I guess I say plasma torch like everybody should know what it is.
Yeah. So, yeah. Like, what are the big limitations, though? Like, what's preventing us from taking those next steps? I guess, what are those next steps, and what needs to be done or researched in order to get there?
Yeah, I mean, like I said, this is I called it semi-commercial, I think, but it's really a lab scale technique. Like, to scale this up, you would almost have to move to a different type of atomization, because to make like a transducer that can vibrate bigger and bigger parts of metal to cause that breakup, it's like, it's technically challenging, I would say. It's hard to scale this up. The real benefit of this technique is being able to explore it at like the small scale, the research level scale. Certainly the influence of like, this powder on how it prints, but also doing powders that don't already exist, right? If I want to buy steel powder, I can do that. If I want to buy a custom alloyed powder, it's either going to cost a lot of money to do that, or it's just not going to be available, right? To get somebody else to make it could be, thousands of dollars a kilogram, right? Whereas now we're not making quite a kilogram, that's not our powder, but we're making maybe that much, really 20, 30 grams, not a lot. But we have the ability to make custom compositions, right? And I guess back to the NASA thing, like where I see the vision and one of their big needs for like future propulsion technologies is high temperature materials. So to make nozzles and nuclear reactor components and stuff like that. I can explain those technologies in a sec, but to talk more about the materials first, you need the high temperature capabilities to make some of these technologies run. But the compositions might not already exist. So this sort of technique would allow us to make custom powders with like really high melting point materials, basically. Things like I said, like tungsten or molybdenum. They call them like refractory metals is the term they'll use. Refractory it literally just means high melting, right?
Group 6 and 7?
Group 6. 5 and 6, 7.
Okay, yeah.
Think transition metals, right?
Okay, sure.
So anything like titanium is not refractory. I don't consider it refractory. That's like melts lower than steel.
Yeah.
But like molybdenum, niobium, tantalum, tungsten, those types of metals. Rhenium, a little more expensive. Things that operate at temperatures beyond steel, beyond the turbine blades of like airplanes. Those are made out of nickel superalloys. Things that really push like the limit of that. The trade-off is that they're really heavy, right?